Everybody asked me how I know. I smiled at them and said they told me so. Everybody asked me.
Hello everyone, I welcome you all to another video on wind load calculation as per IS-875 Part-3 2015. So in this video we're going to calculate the wind load for this structure, and in the previous video we find out that this structure is a rigid structure, so we have to consider the static method. If we get this structure as a dynamically wind sensitive structure, then we have to consider the dynamic method. So right now our structure is a rigid structure, so if you haven't seen that video, do check it now, link is in description. So our structure is a rigid structure, so we're going to calculate the wind load as by using the force coefficient method. So for calculating the wind load, we have to follow 3 steps. So the first step is to calculate the design wind speed. That is your Vz. So this Vz is equals to your Vb into K1 into K2 into K3 into K4. So here Vb is your basic wind speed, K1 is your probability factor, K2 is your terrain roughness and height factor, K3 is your topography factor, and K4 is your importance factor. So the second step is to calculate the design wind pressure. That is PD. So PD is equals to your PZ into KD into KA into KC, where PZ is equals to your 0.6 into Vz square. So here Pz is your wind pressure at height Z, Vz is your design wind speed at height Z, okay, and Kd is your wind directionality factor, Ka is your area averaging factor, Kc is your combination factor. So the last step is to calculate the wind load. So this wind load is equals to your Cf into Ae into Pd, where Cf is your force coefficient, Ae is your effective frontal area, and Pd is your design wind pressure. So let's see how we get these values for these parameters from IS code 875 Part 3 2015. So the first parameter was your basic wind speed. So basic wind speed is calculated using this map. So if you're looking for Delhi, so Delhi is in your green zone. So for green zone, the basic wind speed is your 47 meter per second. You can even find your basic wind speed using annexure A on page number 51. So let me write it over here, 51. Okay, so this is your annexure A. You can find the basic wind speed for some important cities or towns. Okay, so if you want to check for Delhi, so Delhi as the basic wind speed as 47. Even you can check for Ahmedabad as 39, and any other city like Lucknow, it is 47. So you can find the basic wind speed using annexure A or the map of the India. Okay. The another factor was risk coefficient. So we can find the value for risk coefficient using this table 1. Okay, so in this table 1 we have class of the structure and mean probable design life of the structure in years, and basic wind speed. And these are the all the values for your K1. Okay, so let's say our project location is Delhi. So for Delhi, the basic wind speed is 47. So if our structure is all general buildings and structure, then the value for K1 will be of 1. Okay. If the temporary sheds or a structure such as those used during the construction operations, for example, formwork and the folds construction, structure during construction stages and the boundary walls, then uh, then the value for risk coefficient is 0.71. If the building and the structure presenting a low degree of hazard to the life and the property in the event of failure, such as an isolated tower in the wooded area, farm buildings other than residential buildings, then we're going to take 0.09. Okay. If structure is important, building and the structure, such as hospitals, communicating building, towers, power plant, etc., then we're going to take the risk coefficient as 1.07. If the basic wind speed changes, like if it is 39, then we're going to take the values for K1 as 1.76, 0.92, 1.06, according to the class of the structure and the design life of the structure. Okay, so here it is 55, 25, and 100. Okay, so this is how we find the value for risk coefficient. The next parameter was your K2, that is your terrain roughness and height factor. So K2 is obtained from table 2. Okay, so here it is. So in this table, we have this height set and the K2 value for terrain category 1, 2, 3, 4. So before moving to terrain category, let's see this table 2 first. Okay, so here we have this height. So at 10-meter height, we have to consider the K2 as your according, let's say our terrain category is third. So we have to consider as 0.91. At 15, we going to consider 0.97. At 20 meters, we going to consider 1.01. So here you can see it is a cumulative height of the structure. Okay. So if we want to find the value between 15 and 20, like let's say 19.6, then we can find this value using linear interpolation. Okay. For intermediate values of the height set in a given terrain category, use linear interpolation. Okay. So let me move this. So intermediate values can be calculated using linear interpolation. Okay. So now let's move to the terrain category. Terrain category 1 is defined as exposed to open terrain with a few or no obstruction in which the average height of any object surrounding to the structure is less than 1.5 meters. Okay, so terrain category 2 is defined as the open terrain with well scattered obstructions having height generally between 1 to 5, 1.5 meters to 10 meters. Okay, and terrain category 3 is defined as the terrain with numerously closely spaced obstructions having the size of buildings or structures up to 10 meters in height. Okay, and the terrain category 4 is defined as the terrain with the numerous large, high, closely spaced obstructions equivalent to above 25 meters. then that terrain category would be category 4. Okay, so like this we define the terrain category, and using this terrain category definition we calculate the K2 value accordingly. The another factor is your K3, that is topography factor. Okay, so if the upwind slope is below 3 degrees, then K3 is equals to your 1. If greater than 3 degrees, then K3 will lie in a range of 1 to 1.36. And if the upwind slope is greater than 3 degrees, then we can calculate K3 using annexure C. So let us move to the annexure C. So K3 will be calculated using this formula, that is 1 plus C S, where C will be calculated using this criteria, that is if the slope lies in a range of 3 degree to 17 degrees, then C will be equals to your 1.75. Okay, and if it is greater than 17 degree, then it will be equals to your 0.36. Okay, where Z is your effective height of a topography feature. Okay, and L is your actual length of the upwind slope in the wind direction. So for this, you can refer this image, that is 13.8. So here you can see this is your Z and this is your L. Okay, and this is your crust. Okay, and the second parameter was your S naught. So S naught is derived according to C 2.1 at an appropriate height edge above the mean ground level and the distance x from the summit or a crest related to the effective length L. Okay, so this is your h and this distance is your x. Okay, so the factor S naught can be determined using figure 14 and figure 15 according to the condition. Okay, so let's have a look to the figure 14. So this is your figure 14. Okay, so over here we have two parameters, that is h by le and x by le. Okay, and whereas this is figure 15, so this is also dependent on h by le and x by le. So how we find this le? So for that we have to check this criteria. So if the slope lies in the range of 3 to 17 degrees, then le will be equals to your l. And if it is greater than 17 degrees, then le will be equals to your z by 4. Okay, so this is how we calculate the value of K3 in case of greater than upwind slope greater than 3 degrees. Okay, and we will see how we calculate this K3 for this range in the later in the example. Okay, another factor is your importance factor for cyclonic region K4. Okay, so here we find the value of K4 using this data. So basically, it's depend on the structure utility. If it is a structure such as a public structure, more precisely, it is a cyclonic shelter or a hospital, school, communication tower, then we going to consider K4 as 1.30. If it is an industrial structure, then K4 will be equals to 1.15, and all other structures K4 is equals to 1. So this is how we calculate the design wind speed. So basically design wind speed at any height set depends on risk level, terrain roughness and height of the structure, local topography and importance factor for cyclonic field. Okay, so here is your design wind speed at height z, that is your PB into K1 into K2 into K3 into K4. So where PZ is your design wind speed at height z in meter per second, K1 is your probability factor or a risk coefficient, K2 is your terrain roughness and height factor, and K3 is your topography factor, and K4 is your importance factor for cyclone precision. So we see how we find these values for these parameters, and now we can easily calculate the design wind speed at any height set. After calculating the design wind speed, then we calculate design wind pressure. The design wind pressure is equal to your Kd into Ka into Kc into Pz, where Pz is equal to your 0.6 Pz square. So Pz is your wind pressure at height set in Newton per meter square. Okay, and Vz is your design wind speed at height set in meter per second. Okay, and Kd is your wind directionality factor. Area averaging factor is your Ka, and Kc is your combination factor. Okay, and the value of the Pd, however, shall not be taken less than 0.7 Pz. So here the product of Kd, Ka, Kc shall not be less than your point. Okay, so now let's see how we find the value of Kd. So here it is, Kd. Okay, so it's depend on the your shape of the structure. So if it is a triangular, square or rectangular, then the value of Kd shall be zero point 0.9, and if it is circular or near circular, then Kd value should be taken as 1, and if the structure or a region is cyclonic affected region, then Kd value shall be taken as 1, irrespective of the shape of the structure. Okay, so this is how we calculate the value of Kd. So another factor is your Ka, that is your area averaging factor. Okay, so table 4 is used for calculating area averaging factor Ka. So in this table we have tributary area and Ka. So before entering into the table, let's see what is tributary area. So for overall structure, the center to center distance between frames multiplied by the individual panel dimension in the other direction together with overall pressure coefficients. But I'm considering the wind is moving in the x direction, so it is acting in this direction. Okay, so this phase is your Ly and this will be your Lx. Okay, so wind is moving in x direction. Okay, so I'm taking this phase over here. So this is this phase. Okay, so the tributary area will be center to center distance. So this is your center to center distance. Okay, let's say this will be nothing but your story height. Okay, so let's take it as hi. Okay, and this is your lateral dimension, that is your L. So the tributary area will be equal to your hi into L by when wind is moving in x direction. Okay, and in case if wind is moving in y direction, then this will be your hi into Lx. Okay, so like this we calculate the tributary area, and using this tributary area we calculate the value of Ka. So let's move to the table 4. Okay, so if the tributary area is equal to 10, then we going to take the value of Ka as 1. If it is 25, then 0.9, and if it is 100, then we calculate the 0.8. Okay, and if the tributary area in between 10 to 25 and in between 25 to 100, then we going to calculate the value through linear interpolation. Okay, so the linear interpolation for intermediate values of the Ka is permitted. Okay, so like this we calculate the value of Ka. So the last factor is your Kc, that is your combination factor. Okay, so it is over here. So when taking the wind load on a frame of a flat building, it is reasonable to assume that the pressure or suction inside and outside the structure shall not be fully correlated. Therefore, when taking the combined effect of wind loads on the frame, a reduction factor of Kc 0.09 may be used over the welding envelope when the roof is subjected to a pressure and the internal pressure is a suction, or a vice versa. So when we calculating the force load using the force coefficient method, then we consider this Kc value as a 1, and if we calculating the wind load using pressure coefficient method, then we going to consider this Kc as point. So the final step is to calculate the wind load. Okay, so the wind load is calculated using force coefficient method. So the wind load is equals to your Cf into Ae into Pd. So where Cf is your force coefficient, okay, Ae is your effective frontal area, and Pd is your design wind pressure. So we already calculated the design wind pressure. Now we have to see the values for Cf, that is force coefficient and effective frontal area. So effective frontal area is nothing but, so let's consider the wind direction is the x direction. Okay, so, so this dimension will be your Ly, and this will be your Lx. So wind is in x direction. Okay, direction. So the frontal area, if we talk about the top story, then this will be the frontal area. So this is your distance, height, let's say small h, and if the story height is your capital Hi, that is nothing but your 3.2 meters. If we take our example, so the h will be your equals to your half of 3.2. Okay, so that is 1.6 meters. Okay, and if we talk about the intermediate story, then the story, then this will be the effective frontal area. Okay, that is this center to center distance into this Ly. Okay, so let's take this as Hi only, because this will be equal to your Hi. Okay, so for the top, this story, the top story, the frontal area will be equal to your 1.6 times your Ly. Okay, if the wind is in x direction. Okay, and for the intermediate stories, this will be your equal to your 3.2 into Ly if the story height is 3.2. Okay, and if the wind direction is in y direction, then this will be your 1.6 Lx and 3.2 Lx. Okay, so now the last and the final parameter which we have to see is the force coefficient. Okay, so force coefficient for flat buildings. Okay, so the force coefficient for rectangular or a uniform section with a flat roof and uniform floor shall be given in the figure 4. Okay, and for the other flat buildings of uniform cross section without projections, the depth where otherwise shown shall be as given in table 25. Okay, and force coefficient for the building of a circular cross section shall be as given in the table 25. Okay, so this is the figure which we going to use for calculating the CF value. So this is your H by B, okay, and in the X direction it is your AB. So similarly, this is your AB, HB, and AB. So these two figures are, the B is when the HB is less than 1, and if HB is greater than 1, then we going to refer figure A. Okay. So over here, so if wind is moving in the X direction, then B will be your this, and A will be your this. Okay. So in this case, the B will be equals to your Ly, and this will be your equals to your Lx if wind is moving in X direction. Okay. But if it's moving in the y direction, then this is the case. So wind is moving in this direction, so this will be your B, okay, and this will be your A. So in that case, this will be your equal to your Ly, and this will be your equal to your Lx. Okay, so this is when wind is moving in y direction. Okay, so this is how we find this value A and B. Okay, and H is this, the wind height of the structure. Okay, so this is how we find the value of A, B, and H. Okay, and using these three values, we calculate the value of CF using these two figures. Okay, so let's move to the example and see how we calculate the wind load. Now we are calculating the wind load for this case. So we know that Lx is equal to 14 meters, Ly is equal to 15 meters, and height of the structure is 22.4 meters, and the story height of a single story is 3.2 meters. Okay, and rest of the parameters we will assume in the equation. So let's consider the location of the project as data. Okay, so enter B and let's find it. Okay, so there are it is the basic wind speed is 47. Okay, so the class of the structure is all general buildings and structures. Okay, so it automatically taken the cable mass. Okay, so of this speed slope we are considering in the range of 3 to 17 degrees. So let's take it as a pin. Okay, and the height of the crust as 900 meters. Okay, and the location at which we are calculating the K3 value, that is the topography factor, let's take it as 200. Okay, so it will automatically give us the H by LE and X by LE. So we can find this value using figure 14 or 15 according to our case. So right now I'm considering it as a clip. Okay, so using this figure we need to calculate. Okay, so this value was equal to 0.169, and this value is equal to 0.039. Okay, so this value will be lying over here in this, and this value will also be lying over here. So it will lie between these two contours, that is 0.06 and 0.08. So let's take this value as 0.7. Okay, so enter it 0.7. So before that, okay, so zero point 0.7. So it automatically calculated the topography factor. Okay, so structure category, our structure is all of the structures. So the K4 will be 1 and our structure geometry will be rectangular. Okay, so and there is not a cyclonic region. So right now I'm considering no. So the value of KD is 0.09. Right now we are using force coefficient method. So let us enter force coefficient method. So this will be KP will be equals to 1. So in x direction our length is 14 meters. In y direction it is 15. At this height is 3.2 meters. So it automatically gets us the tributary area in x and y direction, and accordingly it calculates the area averaging factor in x and y direction. So height of the structure is 22.4 meters. Okay, so it gives us the value of A by B and H by B, that is 0.93 and 1.4. So we can find this value for finding the value of CFX, because this is an x direction. So we have to use the graph figure number 4, A or B. So right now this for H by V value is greater than 1. So we're going to consider this first case. So in this case, it will be in x direction it was 0.9 something. So it will be very close to this and lies in between 1 and 3. So its value will be somewhere 1.25. Okay, 1.25. And for this value is greater than 1. So 1 point something. So this value will be very close to this one. Okay, and it will lie in between this. So this will be equal to your 1.2. Okay, somewhere 1.2. So this is how we calculate the PFX and PFY. Okay, so now I have to select the terrain category. So I'm considering that the terrain category is open with well scattered obstruction having height generally between 1.5 to 10 meters. Okay, so I'm selecting the terrain category as 2. So now we have to enter the number of stories. So second, so we have 7 stories. Okay, the story height is 3.2 for all. So let me enter it over here. So this is the cumulative height. So now we are finding K2. So we already selected the terrain category as second. So for the values lesser than 10, we have to refer to this table. So we are getting it as 1. Okay, so this will be of 1. This will also be of 1. This will be also be of 1. Now we have to calculate for 12.8 for second category. So this will be of 1.03. Okay, and then this is 16. So let me write 16. So for the 16 it is 1.05. Okay, so 19.2. So this will be your 1.07 for 22.4. So this will be your 1.08. So now it's give us the value of design with speed. Okay, and accordingly design wind pressure at any height slit, and then the design wind pressure in x and y direction. This is the effective height. This is the frontal area in x and y direction, and accordingly it is find the wind load, that is this all are in kilonewtons and kilonewton per meter square. Like this. Okay, so this is how we calculate the wind load for using IS-875 Part-3 2015. So these are the formulas which are used in this Excel sheet. So if you want to know how I have created this Excel sheet, then let me know in the comment box. And if you like the content, then do subscribe to our channel and don't forget to press the bell icon and like and share with your friends. And thanks for watching.